Okay, everyone, I see you are very inspired, but I would kindly ask you to maybe take your seats so we can continue. Okay, so to continue the data analytics and gaming track, I first invite Dmitrii Matveev, the lead data scientist at Wargaming. Dmitrii leads a team of data scientists and analysts that covers a wide range of responsibilities such as controlled experiments, price optimization, marketing mix modeling, causal and predictive modeling, and recommendation systems. He will now give a talk titled Unlocking Revenue, Newcomer Classification for Boosted Profits. Dmitrii?
Hello, everyone. I just want to make sure that floor is not lava. So actually, topic name is a little bit different. But the main point is right. So, does anyone know World of Tanks game? Okay. So, seems like most of you know about Wargaming company. But firstly, let me introduce myself a bit. So, my name is Dmitrii Matveev. I'm leading team of data scientists and analysts in Wargaming. I have a master's degree in applied math, and previously I've been working for a large advertising company. So, all in all, I have more than 5 years in data science and analytics. And about Wargaming, it's a huge game company with more than 3,000 employees and 16 offices across the world from USA to Japan. And most of games are war-themed. Yes, so World of Tanks, World of Warships, but we also have casual games, such as Bowling Crew. So, name speaks by itself. It's a bowling game with different modes, features, and very nice PvP. It's been on the market since 2020, and currently has about 40 million users. So, like every other game, it needs to have strong analytic support. And our data science scope includes conducting A/B testing, build recommender systems, and predictive modeling. And today we are trying to focus on the third point and talk about predictive modeling. So let's look at our agenda. Let's start with the problem definition. Then we review most popular approaches for predicting lifetime value and churn of new users. Talk about losses and the performance evaluation. And finally, about integration, the system into your product. So let's define a problem. In casual game, players tend to be relaxed. They do not perceive game seriously, which results in high churn rate. But among our new users, there are payers, and there are high-value users called whales. And we want to identify this group of players as soon as possible. So here's our plan. Firstly, we acquire users, define high-value ones, predict if this player is willing to leave, and try to retain him. So this is a little spoiler. After implementation of these systems that help us to classify these users and predict their LTV, we already increase our lifetime value by more than 4%. So let's talk about LTV. As you can see, this metric pretty noisy. It has a lot of zero values because most of users are not paying, they have zeros. And on the other hand, about 80% of revenue ensured by small group of users. Actually, we even can't see them. So it's a very little group. So distribution looks like normal, and it's the main challenge in trying to predict it. But as we mentioned before, in casual game, players are not serious. So churn rate is pretty high. And to define churn, we use two periods. First one is observation period, and second one is churn prediction period. As we want to be quick, we have to set our observation period short. So in our case, in just 1 day. And churn period have to be longer because we want to see how our players behave in game. But there is a trade-off. It's always a trade-off. If we set our observation period very short, we run into that our model performance is quite low. So performance is improved by increasing observation period and decreasing churn period. But again, as we want to be quick, we have to set the first period 1 day. And in this 1 day, we have to collect as much information about user as possible. We want to collect all the knowledge about this player. So actually, features can be extracted from different sources. The first one is activity. We can identify it by number of sessions, maybe the patterns in game, transactions, how they play, their win rate, etc. We also have to define some contextual and meta features and understand how players behave in this 1 day. So actually, we use about 300 different features to make our model perform well. So, as we define with the problem with a data, we can think about models we can implement. So we are not going to talk about the most classic one model, buy till you die class model, because we don't have a lot of prior information about users' purchases, because most of them do not pay, actually. And we can use straightforward LTV forecasting with target transformation. And we can sample, add some augmentation to our data by using minority oversampling. So we can use smooth, Decin, and things like this. It doesn't matter, actually. But it's all about lifetime value. We have to predict churn. So we face two-stage machine learning system where the first model predict lifetime value and second, churn. But do we actually want to maintain 2 or more models? Because, okay, we want to predict churn, we can make ensembles and complex algorithm. We can make a Kaggle problem from the simple business task. We don't want it. We want to do 1 model. And with multitask learning model, we can create and train just 1 that help us to predict at least 2 different metrics. But actually, you can put here much more. So intuition under this approach is quite simple. You can see it in real life. So best example is kids. Firstly, kids learn how to recognize parents' faces. And using this knowledge, they understand how to recognize different objects. And you can find such example in education. Firstly, we start to learn simple things and then come to the complex ones to better understand it. So when we deal with multitask learning models, we have two methods. First one is soft parameter sharing, and the second one is hard parameter sharing. In soft sharing, each task has its own model, and distance between parameters are regularized to make them similar. And in hard sharing, well, each task have same high hidden layers, same parameters, but each task has his specific output layer, his heads. So this approach helped us to regularize, to generalize better and reduce the risk of overfitting. And after multiple tests, we stay on this method because it's pretty well. So after we define data, we define architecture that we are going to use. There is a most important part of every machine learning project: loss function. Let's imagine that we have a vector of target policy, like 100, 100, 100, 100, 1000. We have one model, we have same data. And if in first option we use MSE, our output vector will be looking like this. So you can see it here, at 590. And second option is to use MAE. And the output vector of prediction will look like this. So it's 500s. Do you have any ideas why? Okay, well, actually, with the first one, mean squared error, we're optimizing to predict mean. And the second one, mean absolute error, we want to optimize to the median of our distribution. But if we have such highly skewed distribution as lifetime value, which is actually log normal, we don't want to predict mean or median. So in our case, we can take log normal loss function, because we have log normal distribution, right? And optimizing to the mean of this log normal distribution. And in case we have two tasks, first is classification, second one is regression, we can create a mixture loss, where the first component is binary cross entropy loss function, and second one is log normal loss. Well, as we can see, when we use mean squared error, it penalizes, overestimates, and underestimates equally. We don't want it. And log normal penalize, underestimate highly than overestimate. So in our case, we want to predict well users among all our new user set. It's okay to overpredict. It's okay to overpredict values, but it's really crucial to us to not underpredict, because we want to be 100% sure that we classify our users well. So intuition is pretty obvious. We have three parameters. First one is P, which is probability of making purchase or churn. It can be different if you have another business problem. Mu is a mean of our metric, and sigma is standard deviation. So finally, after we understand and define all these things that we mentioned, your neural network architecture can look like this. Actually, it's a pretty old architecture. Currently, we have another one. But it's a nice example, right? So for each categorical value, for each categorical feature, we have embedding layers, and then embedding vectors concatenate with numerical features. We can put it in some dense layers. And then in the end, we have to have the first one is a regression task to predict lifetime value. And the second is for classification. So, well, we built our model. We want to evaluate it, right? So for classification, we use AUK, recall, and F1 score. And for regression, we use MAPE, Gini, and Spearman. Most of them are pretty standard. Yeah? But let's look closer to Gini. This coefficient used by economists to identify wealth inequality in different countries. But wait, we have the same situation in our game with our players. So this helped us to understand how well we segregate our users. And after all model validation, we actually usually want to do this, we calibrate our model. So on the left side of the slide, you can see bad model calibration, where means of prediction and ground truth are not close to each other in different buckets or decile. And on the right one, we see a really well calibrated model. So after pretty hard time of fine-tuning our model, we receive really calibrated, really well model with high performance. And when we create and validate this model, we can start with implementation, and of course we want to deploy it to production. So your scheme can look a little bit different, but of course we have some ML ops system with some integrations, and we want to get model inference from this system, from our pipeline, and put it somewhere where game server can get them and talk to our players in this pipeline. So firstly we receive inference, then we select high value players with high probability of churn, and then we make them exclusive deals. So of course we make lots of A/B testing in this story and understand that the best approach to give players a free gift, not paid, not notification, because currently lots of players just turn off notification. It doesn't make sense. But it can work for you. So let's see. Implementation of the multitask learning model already helped to increase LTV pretty great. The choose and loss function helped us to reduce model error. And model calibration is very important, of course, when you have such highly skewed metric distribution. And you can see it in your online and offline metrics after A/B testing. And also, multitask learning works quite well with multi-gate mixture of experts, so you can try it. Thank you very much for your attention, and if you have any question, I'm ready to answer.
Are there any questions? We have some extra time.
Hi. So when you identify someone as a whale, what do you do? What's your action in the game that makes them have a higher LTV?
Okay, we have two options. Player is a whale. First one, he will into churn, and the second one, he don't have high churn probability. In first case, if churn probability is low for this player, we do not do anything. He just play a game. And on the other hand, if churn probability is high, we make this player deal. We give him a free offer with some items, soft and hard currency, etc.
Thank you.
Anyone else?
Hello. Well, my question is, you are trying to predict whales in your model, and according to my experience, there's a lot of other players that are not whales. How you deal with that imbalanced data?
We use another loss function. Is that it?
Yeah, but when you trade data,
So yeah, I understand what you're talking about. So if we have a very little class of players who actually pay,
yeah.
we can make minority oversampling. We can augment our data set with synthetic data.
So you
but we don't use it.
You don't generate synthetic data. When you say synthetic data, you mean you generate examples for whales or not in your data set?
I mean, so we create another object, another players that are not exist actually. Like in Monte Carlo, you can just generate a lot of objects. But it's one of approaches, and we don't use it because it's pretty bad. So we have our real data. We don't need another synthetic data. And if you take standard loss function, you'll face this problem when you can't predict whales well, because it's very little of them.
Exactly.
So you have to look at your distribution and create loss function that suits best.
Okay, so it ends up to optimize your data with loss function.
Yes, and another one thing, well, we have some players that already invest hundreds, thousands of dollars in a game. I don't know why, actually. And we can make Vincent rising of these values. So we just cut these high values and make them a little bit literal, but they still whales in our data set. But it's not hundreds of thousands.
Okay.
It's a little bit less.
Okay, thank you.
But can you please ask after, because we need to start with the next talk, but I want to thank Wargaming again for being Pandora's sponsor, and of course Dmitrii for his useful talk. And here's a certificate of appreciation.
Thank you. Thank you.